Today we will start with the bending moment and shear forces. Okay. In physics, you have already studied something about bending moment or just generally moment. Okay. What is moment? Moment is nothing but force multiplied by perpendicular distance. Okay. Like this one. See, for example, if I have a bar here, this to this bar, if I apply force here, let us say this force is 10 newtons. If this distance is 1 meter, what is the bending moment? It will bend like this, isn't it? Because of the force, it will bend like this. So, moment is what? Moment of force is nothing but 10 multiplied by 1. So, this becomes how much? 10. What is the unit? 10 Newton meter. Okay. Now, if I have another bar, I have another force over here, same 10 newtons, but the distance is how much? The distance is 2 meters, let us say. So, what is the moment?
So, multiplication.
Moment is equal to 2 multiplied by 10, that is 20 Newton meter, isn't it? Since it is trying to bend the beam like this, we call it as what? Bending moment. Vishwa? This is called as bending moment. Now you see in engineering applications, you come across so many things where you have got many things hanging like this, correct? Many things are hanging, there are columns and some beams are hanging outside. There is weight on that one. Because of that, what will happen if you try to bend like this, isn't it? So due to that, there is bending and there is a bending moment. What is the direction of this bending moment? The direction of this bending moment is like this, isn't it? See? It is in clockwise direction, it is trying to bend the beam. Okay. Now, if you want to hold it stationary, what you need? You need something to act in the opposite direction, counterclockwise, correct? Like for example, now we have a friend here, he's standing here at this side. Now what I am going to do, I am going to have this one in his hand, hold it. See, now see, this is trying to bring him down, isn't it? I just gave a very small one in his hand so that he doesn't have force here. If it is really heavy, then what will happen? It goes down and his muscle has to push it up like this, correct? It has to push it up like this to keep it stationary. So what is the bending moment here? At this point, bending moment is force multiplied by this distance. You agree with me?
Yes.
Okay. Now hold it. I will add one more here. If I am adding one more here like this, what is happening? This force is also trying to bend his hand down, isn't it?
Yes.
This force multiplied by this distance. This force multiplied by this distance. Correct? So that would be the total effort his muscle here, the shoulder is having. That much is to lift it up like this, isn't it? Now it is very light. Just imagine your whole school bag. If I put it here, it is really going to go down, isn't it? He needs to have a lot of strength here. Okay. So in many of our engineering applications, you have forces in terms of tons. You take your car. The car is riding and you have got the axles. Axles are down, isn't it? Because of the forces moving up and down on the bushes and on the pins. How much of forces are coming? Bending moments are coming. Is this clear? So that's why we need to learn the effect of bending moment at different locations. Okay. Now if I say, what is the bending moment here? At this point, what is the bending moment? Force multiplied by this distance, correct? At this point, force multiplied by this distance, understand? If I keep my hand here, what is the bending moment? Force multiplied by this distance, okay? Remember, what did I do now? I used only one force, which is point load. I call this one as point load. It is acting only in one place. See here? It is only acting here straight away. So I can get this distance, isn't it? I can get this distance. By chance, I have something like this. It's too heavy. Let me take this one. Now if I am having like this, so what is the wazn of this one? Let us say the weight of this one is 10 newtons. Understand? The weight of this one is 10 newtons. What I am going to do, I am putting it over here. So where this force is acting now? because I want perpendicular distance, is it not? You know, bending moment is force multiplied by perpendicular distance. Perpendicular distance from where? Min hina ila hina or min hina ila hina? La. It will be assumed that the force is acting through the middle point, understand? Through the center of gravity. If this is the force, then this weight, whatever is the weight of this one, okay, this multiplied by perpendicular distance from where? From the middle point. Remember this, okay? Still are you with me? Multiplied by perpendicular distance. Don't take from here, from the middle point. Understand? This is the perpendicular distance. Okay? If the whole thing is there, no problem. I need to know only the weight of this. It is clear. If I know the weight of this, let us say this is 10 tons. I mean, sorry, 10 newtons or 20 newtons. 20 multiplied by the distance from here to here. Okay? Sometimes what they do, they don't give the complete weight of this. They give by per meter. Understand? Let us say this is how much? This distance may be 20 centi. Let us say. Okay? He can tell you 1 Newton per centi. Understand? 1 Newton per centi means how many centi is there with me? 20 centi. 20 multiplied by 1 Newton. Yani 20 Newton is the wazn of this. Is this clear? Because the distance is 20 centi. 1 Newton is 1 centi. Yani multiplied by 20. So you have 20 Newton. From the midpoint I multiply it. Okay? This is the way I do it. So if I show it, this type of load we call as what? Uniformly distributed load. See, every centimeter is same amount, 1 Newton, 1 Newton, like this. Okay? Uniformly distributed load. Sometimes what happens? It can be varying load like this. Understand? It can be varying load. Initially it is 0 and then you go like this, the weight is increasing. Like you go to the desert, you have sand dune, is it not? Initially there is less sand. As you go, sand is increasing, the weight is increasing, isn't it? So this is uniformly varying load. So you can represent it in different ways. How do we represent it? I will just show it this way. This is a point load, understand? It is acting at one point. Okay, Shabbat? This is W. This is L. Okay. What is the bending moment? W multiplied by L. Correct?
Yes.
What sign, positive, negative, all these things we will see later. Understand? Now, as I showed you this one we call as what? This one we call as uniformly distributed load. Let us say. How do we represent it? We show it this way. Or in some books they also show it this way. In some books they also show it this way. Is this clear? To show it that it is uniform. Understand? So this is called as what? Uniformly distributed load. UDL. Uniformly distributed load. Okay? If this length is L and if this is what? W Newton per meter, let us say. W Newton per meter. So what is the bending moment? Bending moment is go that side. Bending moment is what? Bending moment is come sit here. Yeah, you have to understand the recording. You don't see that. Moment is what? Bending moment is force multiplied by perpendicular distance, isn't it? So where does this load act? This load acts exactly in the middle point, correct? As I said, right? What is this distance? L by 2. You agree with me? This is L, so it is L by 2, correct? L by 2 multiplied by what is the force? W Newton per meter. How many meters are there? L meters are there. Like Ashwin centi I said, is it not? So I will say W into L. This is your load. Okay. Force multiplied by perpendicular distance. Clear? So I can write it as what? I can write it as WL square by 2. Okay. Now here it was how much? WL. Here it became what? WL square by 2. This is what? This is your bending moment. Understand what we are writing here? We are talking about bending moment. And sometimes the load can be varying load. Okay. The load can be varying load. Varying load is usually shown like this. See? It can be shown like this. Is this clear? This is called as what? Uniformly varying load. Is this clear? Where the load will act? We assume that the load is acting through its center of gravity. Center of gravity for a triangle is somewhere here. 1/3 from this side, 2/3 from this side. It's centroid. You have studied in applied mechanics. This is clear, centroid. So it is acting through centroid. And how much is that? Half into base into height. Okay. But anyway, I will just show you that it is acting over here. So all these things what we have shown over here, these are called as cantilevers. Cantilever beam. Cantilever beam means what? It is a beam which has support only on one side, like our hand. Okay? I hold a dumbbell or something, only this has to support, does it? It is going down, so what this has to do? It has to move it up. Is this clear? So this is called as cantilever beam. And there are other types of beams also. I have shown you the loads. Generally in our class, we will discuss about point loads and uniformly distributed loads. Is this clear? Because of the time constraints, we do that. And the same idea applies for uniformly varying load. That is the third group also. So now just let me show you the other types of beams. You already have studied in applied mechanics. There are different types of joints. One is what? Pin joint is there. Roller support is there, is it not? So now let me just show you. If I write a beam like this and I provide a support here like this. It is a knife edge support. Knife edge means what? It is like this. Okay? It is like this. Understand? If I keep something here, see here it is just like a line, isn't it? The contact with this beam is just like a line contact or point contact. Okay? So this is called as simply supported beam. Simply supported beam. Okay. So now what is this length from here to here? You can have the length as L. Right? And the load. As I said, you have different types of loads. You can apply any load. If I apply a point load, let us say I put a point load in the middle, like this. If I apply a point load in the middle, this becomes what? A simply supported beam with a point load. Okay. So now here you can see I have got a beam, simply supported beam. You can assume that this is, though this is not a knife edge, just for the purpose of showing and demonstration I have here, I can apply the load anywhere. Now see here, if I apply the load in the center, when I apply the force over here, this force is supported by whom? This one and this one, is it?
Yes.
I am sitting on the table. For that matter, if I just show you myself, see you have one support here, you have another support here, isn't it? If I sit exactly in the middle, what is my weight? My weight is 75 kilos, understand? So my weight is 75 kilo, my weight is supported by this leg and this leg. How much? Since I am in the middle, equal, is it not? Common sense will say it is 37 and a half this side, 37 and a half this side, correct? Now let us say I shift slightly this side. If I shift this side, what will happen? This leg will take more force, this will take less force, is it not? Now again I shift some more. If I shift some more over here, what happens? More on this one, less on that one. You agree with me? In applied mechanics we have done something similar, isn't it? Now if I go further, Further, if I go over here and I am exactly sitting on this leg, what happens? Everything is taken by this. But remember, little if I do like this, what will happen? This can tilt like this, isn't it? Why? Because there is moment also. Is this clear? For any system to be in equilibrium, you have to have two equilibriums. One is force equilibrium, another one is moment equilibrium. Understand? One is what? Force equilibrium, another one is moment equilibrium. I am holding something in one hand, I am holding something in another hand. Okay? If this is heavy, what will happen? Automatically I will go this way, is it not? So I have to balance both. This we have already studied in applied mechanics. Okay? So when we want to find out the forces, if I sit here, if I sit exactly here, my weight is 3775. How much does it take? How much does it take? This I have to calculate first. Okay? To calculate this, I have to first find out force equilibrium, that is downward force should be equal to upward forces. Okay? And then, because of this, what is happening? There is some bending on this one, is it not? This one is trying to, I am sitting here, my force is trying to bend like this, isn't it? And there is a support which is like this. This is trying to push it up like this. This and this, they should balance. Then only the beam is horizontal. Okay? So with these two equations, we will find out what are the forces there. Okay? This is one part of the problem. But what did we write on top here? We wrote two things. We wrote two things. Bending moment and shear forces. Is this clear? Bending moment and shear forces. First of all, let me, before going to the shear force, let me do for this one. If I call this one as A, if I call this one as B, if I call this force as F. Okay? What will happen now? You will have a reaction here because of this force. There is a reaction here. This reaction I can call as RA, correct? Correct or no? And I can call this reaction as RB. Okay. So for force equilibrium, what should happen? RA plus RB should be is equal to F. Whatever is acting down should be equal to whatever is acting up. You agree with me? Yes. RA for force equilibrium. RA plus RB should be is equal to what? F. Is it not? This is one condition. What is the second condition? I said there should be moment equilibrium also, is it not? For moment equilibrium, what I need to do, now what I will do is, I will take any portion, either A or B, I will take as my reference to find out the bending moment, okay? So now what I will do, I will keep my hand here, see? RB multiplied by L, correct Shubham? This is acting in one direction, acting like this, correct? Counterclockwise, is it not? Counterclockwise. RB multiplied by L. If I take counterclockwise as positive, or the other way, this should be is equal to what? Because there is only one force. F multiplied by this distance. F multiplied by how much is this distance? Since it is exactly in the middle, I can write it as L by 2, is it? Is equal to F multiplied by L by 2. Okay. So what is happening now? RB is equal to, this will get cancelled, this will get cancelled, isn't it? So this becomes how much? F divided by 2. Okay. So if I call these equations with some name, if I call this one as 1, I call this one as 2. Now what can I do? Not here, I will write 2 here. Now I can take this one and substitute in this, right? Yes. I can take this one and put it here. Use 2 in 1. So what we get? RA plus F by 2 is equal to F. Therefore, RA is equal to F minus, you bring this one this side, F by 2. So this becomes how much? F by 2. Since it is in the middle, there is no need for me to do all this. I can logically say half-half, correct? But you should know how we did the job, because in every problem, your loads need not have to be in the middle. They can be on the left side, right side, anywhere, isn't it? Clear? So we just do like this. So you got RA and RB. This is the way we find out the reactions. Okay, Shabbat? This is a simple one. This is only one force here. Now I can have another one just to show you. So I may have a beam. I may have one force over here, F1, and I may have another force over here, F2. So then if you know the distances, again same thing, RA plus RB should be equal to F1 plus F2. And then take bending moments and try to find out the values. Is this clear? Because you will be having numbers for this one, maybe 10 Newton, 5 Newton, whatever it is. You will be able to find out reactions. Is this clear? So this is the first part of the problem. You got my point? Still we did not go to bending moments, understand? We will draw bending moments and shear force diagrams. Why we need to draw? Because in buildings you have got complicated structures, you have beams. So many forces are acting at different points. Is this clear? So what will happen if the loads are like this? What will be its effect on the beam? How the beam will bend? You got the point? See, for example, now you have it here like this. If I keep it like this, I apply force, you can see there is deflection in the middle, isn't it? Bending moment is maximum in the middle, it is trying to bend, correct? Like this. If it is like this, in this fashion, see here. If I am applying force over here, I am holding it tight, okay? See, if I am applying force over here, what is happening? See here, it is bending here, here what is happening? It is going up, isn't it? If you have different forces at different points, at which points you have maximum bending moment, that you need to know, okay? Because of this bending, there will be bending stresses in the beams. Is this clear? That is your next chapter. Like for example, now see my hand. My hand is like this. Very clear, is it not? Now if I am bending like this, what is happening here? See? It is getting compressed, correct? In the bottom, what is happening? It is getting stretched, correct, Shama? See your hand here, bend here. See here, it is compressed. And see here, it is stretched. Because of this, you have got tension in the bottom. In the top, you have got compression. Is this clear? At some point, there is no tension and there is no compression. Where is that layer? All these things we need to find out when we do the design. Okay? These stresses are called as bending stresses. Because of this bending happening, we have got bending stresses in the beams. Is this clear? This also we need to study. Before that, the first one is bending moment and shear force diagrams we have to draw. Okay? Now, how do we do it? What is shear force now? Let us come to the next part. That is shear force. Now, I have this portion. I apply a force here, okay? When I apply a force here, there is a possibility that the material can shear. You know, last time we made the experiment, what is that? You have it here. See here. We applied a force. What happened to the material? The material is shearing here. See here? The material is shearing and going down, is it not? Correct? I applied a force. How much is the force? 100 newtons. So what is the shear force here? 100 newtons, is it not? Because of this 100 newtons, it is trying to shear off. I am not talking about shear stress. I am talking about shear force. Okay? It is shearing here. Correct, Shabbat? It could have sheared here also, isn't it? It could have sheared here also. It could have sheared here also. It could have sheared here also. Anyway, in this length. Okay? This force is called as shear force. You got my point? I applied the force here. Because of this force 100 newtons, shearing can happen at any point, constant. Okay? At any point, from this point to this point, the shearing force acting down is 10 newtons. Okay? Now shear force is acting like this. There is a possibility that shear force can act like this also, is it not? If I put a force here, it can cut and it can take the portion out, isn't it? Correct or no?
Yes.
You have a butter slab, you take a knife, you apply like this, it will shear down, is it not? You turn the knife from bottom, you cut like this, it will cut and shear like this also, correct? So this is shear force, you got my point? Shear force, we have to find out if you have 2, 3, 4 shear forces, how they will affect the beam, that we need to draw the sketches. That's why I told you to bring a ruler and a pencil, okay? Now first let me draw a cantilever. First is cantilever, which is very easy. Let us take a cantilever. I have a force here, W. Okay, and this length is what? This length is L. Now the question. We have to now come to sign conventions. Now I will tell you what are the sign conventions. Which is positive, which is negative. Because forces can act from up to down and from down to up they can act, isn't it? We need to make sure. Is this clear? Which one we take positive, which one we take negative. Is this clear? If I take any point, any center point like this, so this is my reference line, I will keep here. This is my plane, okay? I keep here. On the right side, if I am calculating and looking to do the analysis on the right side, anything acting downward I will take as positive. Okay, Shubham? This is my reference plane. Anything acting right side downward force I will take as positive. Okay? Immediately on the left side you write opposite to this. This is positive. Okay? Only remember the right side. Understand? Don't remember the left side. Right side, if you remember, the opposite of that one is the left side. Okay? If this is positive, this should be positive. Understand? When this is positive, the opposite of this should be negative. Correct? This is negative. On this side, this is negative. There is nothing like negative 10 kilos. Understand? You have 10 kilo. If you take after 10 kilo, it is 10 kilo. You cannot say minus 10 kilo. Correct? The minus sign is only showing you the direction. That's all. Understand? So this is the shear force. This is the symbol for shear force. Any problem, before solving the problem, you first need to write the shear. I mean, this is sign convention. If you write the sign convention, you will never make any mistake. It is just addition and multiplication, subtraction. That's all. Nothing more than this. There is no partial differentiation or anything here. Now coming to bending moment. Anything which is trying to bend the beam up like this is positive bending moment. Just remember, you go to gym and you take the dumbbells, is that not? You are trying to feel heavy, okay? So this is positive. Happiness is positive, understand? Keep your hands like this, means this is positive. Okay? Opposite of that one is negative. Opposite of that one is negative, okay? Put it this way. This is negative. What is this one? Bending moment. Just put your either left side or right side. If it is trying to bend it up, it is positive. Understand? Either left side or right side of the plane. It is trying to bend it downward. Negative. Clear now? Keep the sign conventions. If you keep the sign conventions, it is very easy for us to draw the bending moment and shear force diagrams. Okay? Now before we conclude, let us just draw a bending moment and shear force diagram for this one. Okay, Shubha? For this one. So now let us say this is 100 Newton. How much? 100. Okay? And let us say this distance is how much? 5 meters. How much? 5 meters is really big. This length of the classroom, is it not? If I bring a bar of this length, I ask you to lift like this, can you do it? Well, most of you may not be able to do it. Maybe 1 or 2, maybe. Okay? Why? Because the moment is really too high. Understand? So now, what we do is, when we start to draw the diagram, remember in the examination and even in the class, in the tutorial, don't write anything below your picture. And I don't want to just scribble like this. This has no meaning, you will never understand it, okay? Write it nicely, draw a nice picture, draw a scale. This is a cantilever beam, so what you do, just below this draw lines like this. Thin lines, okay? Now what I will do now, I will call this one as A, I will call this one as B. Okay? Now what is the shear force? Shear force at A. Sorry, shear force at B. I keep my okay. What is this one? Card. Okay. Do you have anything on the right side?
No.
There is nothing, is it? Is equal to 0. So what I will do? I have 0 here. Okay, sure? Now between A and B, anywhere you keep your hand, you keep your right side downward is what? Positive, correct?
Yes.
And how much is this? How much is this? 100 Newton. Come here, 100 Newton. Come here, 100 Newton. Come here, 100 Newton. Come here, 100 Newton. Is it? So what I will say? Shear force between A and between B and A, I will say, okay? B and, or rather I will call this one as A, I will call this one as B, let it be, it doesn't make any difference. Because we are accustomed to say A, B, A for apple, B for bat, correct? So let me write it. So this becomes how much? Plus 100. Okay. Between A and B is how much? Upside is positive, like downward is negative. Okay. Between this it is constant 100. See, 100. This is shear force. This is positive. Okay. Now if I take the plane on the left side, obviously there is a reaction here, isn't it? Because if I hold something in my hand like this, 100 Newton down, this has to provide 100 Newton up, isn't it? Otherwise what will happen? My hand will crash. Correct? So now this will be how much? This will be B, which is equal to 100 Newtons. Correct? R is equal to 100 Newtons, isn't it?
Yes.
So you have like this. So you have 100. You have 100. If I shift to the left side little bit, see here, I will not write it, I will just explain it. Okay. If I just keep my plane here on the right side, what I have got? Mia downward, positive. Mia upward, negative 100. So it becomes 0. I will come back to 0. Okay. This is shear force diagram. Okay, Shubham? Now let us go to bending moment. This is shear force. Let us go to bending moment. Do you want to find out any bending moment here? Bending moment at A is what? Bending moment at B is what? At A, sorry, at A is what? Bending moment at A. You have any force here? Nothing, is it? 0. So I will write 0. Okay. Now do you want to put your hand here? No need. So just straight away go to this point. Okay. Bending moment at B. Or sometimes your teacher in the theory class may be teaching a little differently. Understand? Did they start this or no? Bending moment and shear force. Did they start in the theory class or no? In the lecture they did not start. Possibly in the lecture class they will start like this. I will show you. They may put a plane here. They will call this one as X. Okay. They may show it this way. Let me write it that only. Bending moment at xx is equal to what? Force multiplied by distance, isn't it? W multiplied by x, correct Shabbat? force multiplied by distance. So how it is doing? It is trying to bend the beam down, isn't it? So what is this symbol? It is negative, correct? It is trying to bend the beam down, right? So it is negative minus Wx. So now in our case we know the value minus, when x is equal to 0, what is bending moment? 0, that is at this point, okay? When x is equal to L, bending moment is how much? Minus W into L. What is the value of W? 100 multiplied by L is how much? L is comes up. That is minus 500 Newton meter. Correct? 500 Newton meter. It is 0. And then you come over here, it is minus. Downward we have taken as minus. Minus 500 Newton meter. This is shear force diagram, this is bending moment diagram. This is negative, this is positive. This is clear. This is a simple problem for shear force and bending moment. Now by seeing this picture, you can very clearly see what is happening. You can very clearly see the bending moment is gradually varying, isn't it? From 0 it is going to some value, okay? What is the equation? W into x. It is something like y is equal to mx plus c, your straight line equation, understand? The power of x is 1. The power of x is 1, okay? When the power of x become 2, it will become what? It will become a parabolic curve, okay? We will see it later. Uniformly distributed load we will see. So now this is shear force. You see, with only one force you have a constant shear force, isn't it? And what is the bending moment? Gradually it is increasing. See that? Same thing. You hold something in your hand. If I hold this one in my hand, my God, it's really heavy. Okay. See, if you hold it here, well, it's really heavy. See here. It looks so small, but it's really heavy, okay? If you want to punish him, you will tell him, okay, count up to 100. How they will say, teacher, forgive me. See, already he is shaking. If it is here, see, by the time if it is here, it is already less effort here, isn't it? If it is here, effort is less. Is this clear? If it is here, effort is less. Is this clear? That's what is happening. As you come closer with the force, the effort will be less. As you move away, what will happen? The effort here is really heavy, okay? That's why you can see when you go outside, just check. Many times you go and park your cars. How is the shade? You have got a shade. You have got a pipe like this, isn't it? You have a column anyway. You have got a pipe like this, correct? And then you put another pipe like this. It looks like a triangle, you can see, correct? Or sometimes you will put a cable to hold it like this, isn't it? Because as you come closer, the bending moment increases because of this. Okay? That's why you can see. This is a straight line. Remember y, the power is 1 here. See, x to the power of 1. The equation is like y is equal to mx plus c. Mathematics. I don't want to go into it. Clear now?